Hello grade 12s and welcome to this lesson on exponents and surds. By now we are very familiar with exponents and surds, but it helps to revise all that we know. Let us join Tebogo as his teacher helps him with this revision.
Hi Tebogo, what are you up to today?
Hello, I'm actually busy with the worksheet on exponents and surds.
And how are you doing?
I'm actually struggling a bit.
Mind if I have a look?
Not at all.
Let's start at the beginning with the laws for exponents. Do you remember what they are?
I can remember some of them. If you multiply like bases, you add the exponents. If you divide like bases, you subtract the exponents. Anything raised to the power of 0 is equal to 1. And if you raise a power to a power, you multiply the powers. If two bases are all raised to a common power, then both bases take the power. I'm afraid that's all I remember.
That's not too bad. You've only left out the last two laws. If you have a negative power, you divide 1 by the base, and then you can make the power positive. And if you take the root of a number, you divide the powers. Now that we have all the laws at our fingertips, we can move on to using these laws to simplify expressions. We can start with this example. Tebogo, what do you think our first step should be?
I think we should start by simplifying whatever we can that's inside the bracket.
That's a good place to start. And how are you going to do that?
The only thing I can see are these bases here that have negative powers. We can simplify them by using one of our 4 laws. The law says that if you have a negative power, you divide 1 by the base, and then you can make the power positive.
Well spotted. Can you do that for us?
Sure. We can write this 4 to the negative 1 as 1 divided by 4, or a quarter. 9 to the negative 1 is the same as 1 divided by 9.
That leaves the fractions in the bracket. Do you think you can simplify the fractions?
Sure. To start off with, we need to collect the fractions in the denominator. To do that, I need to put them both over the common denominator, which in this case is 36. Now we collect the fractions, and we get 5 over 36. This leaves us with a fraction divided by a fraction. So we invert and multiply, and when we simplify, we get 36. I think I can simplify this even further.
Go ahead.
36 is the same as 6 squared. Now, one of the laws say, if we raise a power to a power, we multiply the powers. Here that would be 2 times half, which is equal to 1, which leaves us with 6.
Well done. There is another way you could have approached this example though. We could use the converse of our law, which state that if you take the root of an exponent, you can divide the powers. In this case, your powers are already divided, which means that you can take the root of the exponent. This will give us the same answer as before. Let's try another one.
First, I look inside the brackets to see if there's anything I can simplify. Doesn't look like there's anything.
Are you sure?
Yeah, I think so.
What about 16? Since we are working with exponents, it is often easier to break numbers down into their prime factors raised to the necessary powers. This allows us to group and simplify like bases if there are any. We can do this by using what is called the ladder method. Here, let me show you. 16 can be divided by the prime factor 2. This gives us 8. 8 can also be divided by 2, leaving us with 4. Again, we can divide by 2 and we are left with 2. Lastly, 2 divided by 2 is 1. So 16 is 2 multiplied by 2 multiplied by 2 multiplied by 2, or 2 to the power 4.
Thanks, that really makes it a lot easier to work with. Now if two bases are all raised to a common power, then both bases take the power. Also, if you raise a power to the power, you multiply the powers. So, we get 2 to the power 4 times 3 over 4, and x to the power 4 times 3 over 4. If we simplify the powers, we get 2 to the power 3 times x to the power 3, which is 8x cubed.
Good work, Teboho. You're quite good at this. Let's try another one.
Okay. This one looks really difficult. I'm not sure if I can do it. Where's the equation?
Don't panic. You can do this. Just take it one step at a time.
Okay. The first thing I need to do is write the bases as prime factors. 6 is 3 times 2. 12 is 3 times 2 squared. Now I need to get rid of the brackets. So I distribute the powers. That gives me like bases at the top and at the bottom. I'm not sure what to do first.
It would be easier if you simplify the numerator and the denominator before you go any further.
All right. If you multiply like bases, you add the powers. And I end up with 2 to the power 6x times 3 to the power x minus 1 at the top. At the bottom we get 3 to the power x times 2 to the power 6x.
Now you can apply the second law. If you divide like bases, you subtract the powers.
6x minus 6x is 0, giving us 2 to the power 0. X minus 1 minus x is minus 1, leaving us with 3 to the minus 1. 2 to the power 0 is 1, and 3 to the negative 1 is a third. So the answer is 1 over 3.
See, it wasn't as hard as you thought.
Yes, you were right. I just have to take it one step at a time.
That's right. Now, can you quickly tell me what the exponent laws are again?
Sure. If you multiply like bases, you add the exponents. If you divide like bases, you subtract the exponents. Anything raised to the power 0 is equal to 1. And if you raise a power to a power, you multiply the powers. If two bases are all raised to a common power, then both bases take the power. If you have a negative power, you divide 1 by the base, and then you can make the power positive. And if you take the root of a number, you divide the powers. I'm just looking at these laws again, and I've noticed that we haven't tried any examples which use this last law yet. If you take the root of an exponent, you divide the powers.
You're right. I've been saving that one.
Saving it? Why?
Well, this law is not only an exponential law, it is also one of the Surd laws. I thought it would be better to take a closer look at this law when we were working with surds, which we can do now.
What is a surd exactly?
A surd is a number written underneath a root sign. We use it in maths to accurately represent an irrational number.
And are there rules for surds like there are rules for exponents?
Yes, that's right. But in this case, there are only 3 laws you need to remember. The first law says that if you multiply surds with the same root, you can multiply the bases and put them under the same root. The second law says that if you have a fraction under the root sign, you can take the root of both the numerator and the denominator separately. And the last law you've already seen. If you take the root of a number, you can divide the powers.
I think I can remember those. Let's try some examples.
All right, but before we do that, there are a few things you need to keep in mind when dealing with surds. Firstly, you must always manipulate surds into their simplest form. In other words, you must write them in their prime factor form. Secondly, you can only collect like surds. And lastly, you should never leave a surd in the denominator. You must always rationalize the denominator.
Now you've lost me. How do you know which are like surds, and what does it mean to rationalize?
Would you say that root 18 is in its simplest form? In other words, is 18 a prime number?
No, it isn't.
Okay, so to simplify 18, we would need to write it as a product of its prime factors. Do you think you could do that?
I think so. 18 is the same as 9 times 2. 9 is 3 squared. So that's the square root of 3 squared times 2.
Almost there. What would happen if you applied the first surd law?
Well, we'd get the square root of 3 squared times the square root of 2.
And what is the square root of 3 squared?
It's 3. Ah, I see. If I apply the law, I get 3 root 2.
And you'd have written root 18 in its simplest surd form.
Can I try another one?
Here, try this one. Remember that you must always write a surd in its simplest form first.
50 is 25 times 2, and 25 is 5 squared. If I apply the first law, I get the square root of 5 squared times the square root of 2, which gives me 5 root 2.
Good, Debuho. Now, let's look at the next one. You can only collect like surds. Like surds are similar to like terms. You can add x and x to get 2x, or y squared and 2y squared. But you cannot collect x and y squared. So, similarly, you can add root 2 and root 2 to get 2 root 2. But you can't collect root 2 and root 5. It's important to remember that the law only applies when you are dealing with like surds. But if we are multiplying the unlike surds, we can convert them into like surds. To do this, we use this formula. It says that if we multiply the root and the power by the same number, it doesn't change the value. We use this rule in a similar way to using the common denominators, in that we use it to get the common powers to simplify the equation through grouping terms. Here's an example for us to try. In this example, we have a third root and a fifth root. The easiest way to convert them will be to multiply 3 by 5 and 5 by 3 to get the 15th root for both of the surds. By doing this, we have converted unlike surds into like surds, and now we can apply the laws and simplify. Do you think you can take it from here?
The first law says that if you multiply surds with the same root, you can multiply the bases and put them under the root sign. So let me do that. Now I can use my calculator to work that out, which gives me the 15th root of 30,375, which is irrational, so I'll leave it in the surd form.
Nicely done, Debuho. Let's move on to the next rule. Never leave a surd in the denominator. You must always rationalize the denominator. As we said, a surd is an irrational number. It's easier to work with fractions when they have a rational denominator. When we do this, we say we are rationalizing the denominator.
That makes sense, but how do I do this?
Here, I'll show you. Tell me something, Debuho. What do I get when I multiply root 2 with root 2?
That will be root 2 squared, which is 2.
And 2 is a rational number, while root 2 is not. So, by multiplying a surd by itself, we would get a rational number. But if we did this, we would change its numerical value. We know, though, that if we multiply a number by 1, we don't change its value. And any number divided by itself equals 1. Now, if we combine these two principles, it gives us a method of rationalizing the denominator in a fraction.
Okay.
Here, let me show you. In this example, we have root 2 in the denominator. I want to change this root 2 into a rational number, but I don't want to change the numerical value of the fraction. In other words, I need to somehow convert this fraction into an equivalent fraction with a rational denominator. I know that if I multiply a surd by itself, it gives me a rational number. So I'm going to multiply this fraction by root 2 over root 2, which is 1. And as such, doesn't change the value of the existing fraction. And if I now apply the first law, it gives me root 10 divided by 2. 2 is a rational number, so I've rationalized the denominator.
Hey, that's pretty clever.
It is, isn't it? Would you like to give it a go?
Yeah.
You can start with an easier example.
The denominator is root x. So I multiply the fraction by root x over root x. Then I apply the first law, which gives me the square root of x squared y over x. I simplify this, I get x root y over x, and the x's cancel out, leaving me with root y.
I'm impressed. Now, can we try one that's a little bit more difficult?
I'll give it a try. There's a root y in the denominator. This means that I need to multiply the whole fraction by root y over root y. In the numerator, I distribute the root y into both terms to get 5x root y minus 16 root y. In the denominator, root y times root y equals y, which is a rational number.
Excellent, Deborah.
Thank you for joining us, grade 12s, for this revision of Exponents. You will find more questions on this work in the exponential and logarithmic functions task video. You will also learn more about logarithms and exponents on our website www.mindset.co.za/learn. Goodbye.